Hello everyone, once again, welcome to a new lecture. In previous lecture, we discussed about the working of EMC meter and its application as a power measurement tool for AC as well as DC sources. As we see in DC sources, it will directly measure the power as a particularly multiplication of V and I, where when we measure the particularly AC power, or we say true power or active power, it does not mean as an instantaneous torque. It does not be directly measure the AC power. We have to be aggregate it torque, its aggregated torque, or we say we have to be average the average torque, calculate the average torque, so it will be directly proportional to the true power of the system. And we managed to talk about the different type of application as a EMC meter for a meter as a voltmeter. Now in today's lecture we will in description we will talking about its construction as a electrodynamic type wattmeter. We will discuss that the two coils EMC meter have. One is your fixed coil and other is moving coil. We will suggest that the particularly fixed coil that is represented in this particular figure represented CC or current coil, and PC as a your potential coil or potential coil. Here the fixed coil carrying the current given to the load, and the potential coil is measure the voltage across the load in the system. Here we suggest also that potential coil having the non-inductive type of resistance in it. Okay, now so for this particular type of EMC type wattmeters, let's start the construction features of EMC meter, where first is a fixed coil. It is a two fixed coil. One fixed coil can be having the symmetrical arrangement, carrying the current of a your load. This particular coil is divided into two sections, basically forming a uniform magnetic field near the center to allow the placement of instrument moving shaft. The winding of this particular two fixed coil is normally made of standard conductors, and they are insulated from each other. All the strands which are brought to the from the external communicating terminators are in series or can be parallel, depending upon the what type of commutating practical you should wanted from this. This stranding of fixed coil are reduce the AD current losses, as we discussed in previous type of instruments also. This higher current or voltage range of accommodation only through the use of instrument transformer. Now talking about the second part, it is called moving coil system. Moving coil system is used for measurement of voltage as a pressure coil. This particular current through this particular moving coil or pressure coil is proportional to the voltage. So we will also call this as a voltage coil or pressure coil or voltmeter. It is entirely impedance by the fixed pair of coil. It always say it is in between the two fixed coils. This particular coil is very highly non-inductive resistance, isn't connected with the voltage coil to restrict the current to the small value. As you wanted that voltage practically, as we'll discuss during the systematic arrangement, that in case of loading effect, voltmeter also act as a load. So for reduction of a loading effect error, we have to be increase the resistance of a voltage coil as much as higher, so it is very small current or a milliampere or microampere current to flow to the only voltage coil. So we ensuring particular type of thing. It is basically this particular moving coil, as we wanted it should be higher resistance. So as we wanted the voltage coil having the higher resistance, R is directly proportional to rho LA. For higher resistance, length of the coil should be high. Okay, for higher resistance, length should be high and area of cross section to be low. So for this, as you see in particularly this type moving coil system, the number of wound coils are very large, and the number of windings in moving coil are large, but its cross section area is very small. Okay, that should be, or we say we use the fine wire system, where in case of your fixed coil, where we wanted ammeter having the very low resistance path, so we wanted the resistance to be low, so its area of cross section, or we say its wire having the thickest of diameter, and length should be small. So we have a small turn ratio with thick wire in ammeter case, in case of fixed coil system. And another thing that is called moment for restoring system. For a moment, as we put the uh, potential coil in a moving system, as there is some torque producing during the interaction of fixed coil and moving coil, the moving system should be made such that it should be connected to a pointer using some aluminum spindle in case of dual bearing to support the spindles. This particular movement or series moving system, it should be higher sensitivity, so such that we will require the moving coil to be suspended from a torsion hold, or we say by a metallic suspension system. This particular suspension system is made of a silk fiber together from a for use of a spiral spring, for such that as we use the phosphorus bronze spring that leading the current toward the moving coil system, it will act as a restoring system also. In any cases, this torsion head with suspension or a spring also serves providing the restoring cases in different type of EMC instruments. Now, two system mode. The first is damping system, second is shielding system. Normally, in case of damping system, we use the air friction type damping. So EMC instrument normally use the air friction type damping. Okay, this damping provides a small aluminum wheel where the last string of a particularly spindle is connected toward its vein. When these veins are made to move inside the closed air chamber, there should be if there is a friction losses happen near it. The AD current damping, however, we cannot use in this type of instrument, because if we use AD current damping, it distort or interfere the operating magnetic field, or we say fixed magnetic field. So we only used here the particularly air friction damping. Now, in case as we see in PMC instrument, permanent magnets have the highest magnetic, having the strong magnetic field in case of PMC meters. But in case of EMC meters, as we use the electromagnetic coil for as a magnetic field, so this electrical fields are being weak, so we provided some shielding system so that the external magnetic field, or we say some outside field, does not affect the working of a system and causing some error affected. So in case of even the earth magnetic field can pollute the measurement of a reading, it's such type of system. So enclosure of such system are will be required with high permeability to restrict the penetration of stray magnetic field also. Okay. So one of the operating system, always we discuss in previous diagrams also, where we say that V and I are the voltage and current to be measured for a load, and IP is the current flowing in pressure coil, and IC is the current flowing in the current coil, where RV is the inductive voltage or a resistance that will be connected in series with resistance, such that we do wanted that the inductive coil or a potential coil having the highest resistance, it does not wanted any particular voltage current to be flowing through it. And RP is the small resistance of a overall coil. RP is basically, it is a resistance of potential coil plus external resistance what we added to it. Okay, now we will see what is the effect of this RV in particular next lecture also, where M is a mutual inductance between the current coil and potential coil, and theta is a deflection that will cause the moving system to move, and omega is the angular frequency which will in case of AC system what will supply from the supply end, and phi is the phase angle lag between current from our source side and voltage that should be applied across it. Now, as we know the famous instantaneous torque equation, that is IC upon dm by d theta, as we know the voltage applied across the pressure coil is root V, as V is the maximum voltage, V is the RMS voltage, so it is root V sine omega t, so it causes to be a maximum voltage. It is a root V because we wanted should be the maximum voltage, where V is the root RMS value only. If the potential coil has resistance can be assumed very high, we assume that pressure coil has very high resistance, then the current in pressure coil is represented by Vp upon Rp. As we see in that, Rp is the total resistance of the pressure coil in addition with the external resistance. Then we can dictate that its overall current flowing through this pressure coil should be root of Ip sin omega t, where the RMS value of current can be given as Ip. V is the RMS voltage and Rp is the resistance of the system. As we also note, phi is a phase angle that should be, we assume phase angle between the current flowing through the load and the voltage. Then the IC, the current coil current, can be root I sin omega t minus of phi. Phi is a angle lag. We will assume that V is voltage, V is in the zero axis, and current I is lag some phi angle behind it in this particular field. Now, this instantaneous torque Ti in this particular system, using this particular equation, we will assume that is Ip, put it there, and IC we will also put there. Now, the equation to be root Ip sin omega t root I sin omega t minus dm by d theta. Okay, now this both root 2 and root 2 multiply to be 2 Ip I sin omega t minus 5 dm by d theta. Now this act as a sin A minus B. Okay, the sin A sin B formula. So we calculate sin A sin B by cos phi minus cos A plus B cos A minus B formula. We will calculate as cos phi minus cos 2 omega t minus phi, where it will indicate that in the instantaneous torque formula or calculation of a power, there should be double frequency of a voltage term. It will indicate that it varies as a frequency of voltage and current. Now we will average this particular instantaneous voltage over a time period, or we say 0 to 2 pi, where when we average this particular value, the final result after this, all the derivation, all this particularly time period integration 0 to 2 pi, we will have Vi cos phi Rp upon dm by d theta. Okay, as we considered. So as we know, what is the value of power? Vi cos phi, active power, and Rp is our resistance of a potential coil, when dm by d theta is our variation due to the inductance effect. Now if with that is a formula, that is Vi cos phi Rp upon dm by dt. If we assume that we will using the spring control system at some steady state, Tc equal to t theta, so k theta is equal to Vi cos phi Rp upon dm by d theta. Now putting the k constant here, now theta is equal to Vi cos phi Rp upon dm by d theta, where we assume that Vi cos phi is the active power system, and we will assume we will indicate the P outside the bracket. So its all value 1 upon Kp upon Rp. This particular whole value, as is the resistance, it should be act as a constant value. It is a K1. It is act as a K1 and dm by d theta. At the steady state, thus it found that this indication theta is directly proportional to P. If we only assume that dm by d theta is constant in nature, as the deflection should be very, mutual inductance should be constant. In that particular case, we assume that deflection occur in case of electromagnetic induction is will be directly proportional to your power or true power. So it is one of the effect that we have to be seen in this particular continuous lectures. Okay, we will also indicate it is one of the major error. Okay, we will only assume that this particular dm by d theta is constant, one thing. Second, we also assume that this Rp is a constant value. Now in next lecture we will see how these two things can cause major error in calculation of true power in case of EMC type wattmeter. Until that, thank you so much for this particular lecture. We will continue this lecture for error of measurement.